Hello, and welcome to this pre-talk. My name is Grace Work, and I will be the mentor for those of you reading the paper, Strict Ergodicity and Transformations of the Torus by Furstenberg. In this pre-talk, we'll be going over some of the background definitions and theorems to help you prepare for the talk Jayadeva Threya will be giving at the Learning Conference next weekend. As I mentioned, my name is Grace Work. I am teaching faculty at the University of Wisconsin-Madison. You can see my email on the screen, grace.work@wisc.edu. Feel free to email me with any questions or to introduce yourself. I look forward to meeting with you this semester. So let's begin this talk by examining the setting that we'll be in and defining some of the basic objects we will be considering. So, our setting. The first space I want to define is something called a measurable space. And a measurable space consists of a pair, X, a set, and B, a sigma algebra. Let's define a sigma algebra. This is a collection of sets that satisfy number one, the empty set must be not an element, must be contained in our set B. Our set B must be closed under complements and closed under countable unions and intersections. In particular, or as a remark, if X is a topological space, then the Borel sigma algebra is the smallest sigma algebra. Containing all the open sets of X. So if we have our pair set sigma algebra, we get a measurable space. And if we add to this and make it a triple, a set, a sigma algebra, and a measure, we get a measure space. And in particular, if the measure of X is equal to 1, then we have a probability space. All right, so this is our space that we're working with. In addition to this space, we'll also be talking about transformations, T from the set to itself. So this T, we'll call this a transformation. And then there are two types of transformations that we want to highlight and define separately. We will have a measurable transformation. And what this will mean is if for all A in this sigma algebra, the pre-image of A is also in our sigma algebra. And saying this in words, the pre-images of measurable sets are measurable. In addition to measurable, we could put another condition on our transformation, which is measure preserving. And a transformation is measure preserving if, first of all, it is measurable. So if measurable, and if the measure of the pre-image is equal to the measure of the set. And if this is true, then we say that mu is invariant under this transformation T. All right, so these types of transformations, measurable and measure preserving, are going to crop up again and again. And one question that we might ask will be to ask, how can we check that a measure mu is invariant under some transformation T, or how can we check whether or not T is a measure preserving transformation of the measure mu? By this definition, it would look like we have to check every single measurable set, but fortunately, that's not the case. So fortunately, we just need to check for subsets of R. We would need to check intervals. For R2, we would need to check rectangles. And for the circle, we would just need to check arcs. Okay, so being able to check these specific collections, intervals, rectangles, and arcs, allows us to avoid having to check every single measurable set. So let's look at an example. All right, example. And we'll be carrying this example of circle rotations through for a lot of the other concepts we'll be looking at. All right, so we're going to define it as R sub alpha. It's going to be a rotation of the circle to itself. And the measure we're going to be considering is lambda Lebesgue measure on S1. And this Lebesgue measure is the same as the one-dimensional Lebesgue measure on just the interval from 0 to 1 under the identification that takes like 0 and 1 and identifies them together. So you get a circle. So we have our rotation, we have our measure. Let's let A be an arc. This answer to the question above says we just need to check that this measure, the Lebesgue measure, is invariant under this rotation on these arcs. So the Lebesgue measure of this arc is going to be arc length divided by 2 pi, so that the measure of the circle S1 is equal to 1. All right. if our rotation of alpha is a counterclockwise rotation by 2 pi alpha, then the pre-image of alpha, or R inverse alpha, is equal to R of minus alpha, and this is a clockwise rotation by 2 pi alpha. And we're taking an arc of a circle, we're rotating it around. Arc length isn't going to change, so the Lebesgue measure of the pre-image of our arc is going to equal the Lebesgue measure of our arc. And we said we only had to check it on these arcs. So in this case, Lebesgue measure is invariant under the transformation circle rotation by alpha. All right, so those are some of our basic definitions. Let's move on to some theorems. And the first I want to talk about is Poincaré recurrence. And I realized I meant at the beginning to give you a reference for some of these things. So if we scroll up, one of the references you can look at is the book Introduction to Ergodic Theory by Peter Walter. So let me write that down. An introduction to ergodic theory by Peter Walters. Okay. All right. Go back to where we were, which was at Poincaré recurrence. Let's define first what it means for a point to return to a set. So here's a definition. Let's consider a subset of X. We say a point in B returns to B if there exists a number k greater than or equal to 1 such that we take the transformation, apply it to our point k times, we're back inside B. We say X in B is infinitely recurrent with respect to B if it returns infinitely often to B. And what that means sort of in terms of this transformation and its iterates, BIE, there exists an increasing sequence Kn and in the natural numbers such that T Kn of X is in B. Okay. So we have this idea of returning to a set and recurring infinitely often to a set. All right. So our theorem, Poincare recurrence, is the following. We have a probability space and we have a transformation that's measure preserving. And we consider a set inside our sigma algebra with positive measure. Then almost every point in B is infinitely recurrent with respect to B. And what we mean by this almost every means, i.e., the set of points X in B that return to B only finitely many times has measure 0. All right. So you have a probability space, this measure preserving transformation, and almost every point in this set B is infinitely recurrent with respect to B. Okay, so let's look at the proof of this statement and try to get a sense for why this might be true. So the main idea for this proof will be what's written in blue over there. Let's look at the set of points that return to B only finitely many times, and let's prove that it is a measure 0 set. So let's let A be the set of points that do not return to B infinitely many times. We want to prove the measure of A is equal to 0. So we can write A as the set of all points in B such that there exists some value K greater than or equal to 1, such that whenever N is greater than K, T to the N is not in our set B. Okay, so there exists some value where after this point, the T to the nth iterate, or T to the N of our point X no longer lives in B. It only returns finitely many times. And this would be for all x, sort of another way to think about this is for all for all n sufficiently large, we have Tn of x is not in B. Okay, so we've defined our set A. Now what we're going to do is kind of look at level sets of A or sets A sub k that separate out specific values. So let's consider A0 should be the set of all x in B such that Tn of x is not in B for all n greater than 0. And let's also define other sets, A sub k, which will be t to the minus k of A0 for k greater than or equal to 1. All right, so we have these A0, we have these AKs. What does this mean? So if our point is in t to the minus k of A0, then t to the k of our point must be in A0, which means t to the k of x must be in B by our definition of A0. But t to the n of t to the k x, which is t to the n plus k of x, is not in B for all n greater than 0. It's just by the definition of what it means for t to the kx to be in A0. Thus, we can describe our a to the k as the set of all x such that tk of x is in B and t to the n of x is not in B for all n greater than k. All right, then we have that A is equal to the set of B intersected with the union from 0 to infinity of all of these A sub k's. All right, so let's look at why this equality is true. So if we're over on this side over here, and if we have x in A, then all we need to do is find an A sub k that x lives in. So then we'll show this on this other side of the equality. So let's let k be the largest integer such that t sub k of x is in B, then x must be in A sub k. And if we think about ourselves on this other side, if x is in this intersection for some k, then t to the n of x is not in B for all n greater than k. Excuse me. So X can return only finitely many times. And therefore, it belongs to A. Okay. So if we're in our set A, we must also be in that intersection. If we're in this intersection, we must also be in the set A. All right. So since we have that A is equal to this intersection, we have that A is a subset of this union we have on the side. So note, let me change back to black marker. Note that A is a subset of this union. So in particular, the measure of A is going to be less than or equal to the measure of this union. So now it suffices to prove that the measure of this union is equal to 0, and then we'll have shown that the measure of A is equal to 0. Each one of these A sub k's are piecewise disjoint. So if I'm looking at the sum from k equals 0 to infinity and of the measures of each of these, and I meant they're pairwise disjoint, this is equal to the measure of the union of all of the A sub k's. This has to be less than or equal to the measure of our whole set X, and this measure is finite. Okay, so the sum of an infinite number of things must be finite. In addition, the measure of AK is equal to the measure of A0 for all K. Since T is a measure preserving transformation, AK is equal to this, and T is measure preserving. Thus, the measure of A0, which is equal to the measure of AK, in order for this sum to be finite, when we're adding up infinite number of things that all have the same measure, all these measures must equal 0 for all K in N, and therefore the sum of all these measures is equal to 0, and thus the measure of A must also be equal to 0. So the set of all points that do not return to be infinitely many times, so they return only finitely many times, or 0, has measure 0. Therefore, almost every point in B is actually infinitely recurrent with respect to B. So that's the idea for our Poincare recurrence. Let's move on to ergodicity. All right. So again, let's start off with a definition. We will say a measure preserving transformation T on a probability space X beta mu is ergodic if and only if for all A in our sigma algebra such that our set is invariant under the transformation, either the measure of A is equal to 0 or the measure of A is equal to 1. And if we want to put it in words, we can think of this as saying all invariant sets are trivial from the point of view of measure. Okay, so this is what it means to be ergodic. The set is invariant under a transformation. It must either have 0 measure or full measure. So let's look at the example of circle rotations again. And we will show that rational rotations are not ergodic. In order to prove something from this definition is not ergodic, it means you would need to construct an invariant set that has measure not equal to 0 or 1. So we're looking at, again, our rotation, which goes from S1 to S1. And we're looking at a rational rotation, so where alpha is equal to P divided by Q, P and Q co-prime. All right, let's define a set A to be the union from I equals 0 to Q minus 1 of this interval, I over Q to I over Q plus 1 over 2Q. All right, let's draw a little picture. So here I have my circle. And let's let Q equal 8. So we're going to divide our circle up into 8 segments. It's not, it should be 8 even segments. And what we're looking at with this set A, sort of these intervals that go halfway around. Okay. All right. So this highlighted intervals around the circle, these are the intervals, and this collection is A in this example when Q is equal to 8. And so if we're looking at, this rational rotation around here, our set A is going to be invariant under a rational rotation. But when we consider the measure of this set. I'm adding up all of these lengths here, all of these shaded lengths. And what we're going to get is that the measure of this set is actually equal to 1/2. So we have a set that is invariant, but when we take the measure, we're getting something that is not 0 or 1. Therefore, our rational rotation cannot be ergodic. All right. So even though the rational rotations are not ergodic, in a second we'll see that irrational rotations are ergodic. And to get there, we actually need to look at another characterization of ergodicity. So here's a lemma. And we will say a measure preserving transformation T is ergodic if and only if any measurable function f from x to r that is invariant which means f composed with t is equal to f, is constant. So this is another characterization. And let's look at the proof of why this would be true. So let's start the proof. Let's look at this direction first. So if we're looking, oops, I apologize. So if we're looking at that direction first, which means we have any measurable function we want. If it's invariant, then it is constant. We'll want to show that if we have a invariant set, then that invariant set is going to have measure 0 or 1. So let's let A be an invariant set. And we're going to consider this measurable function we're going to consider is its characteristic function. Okay, so let's first check. If I take the characteristic function, pose it with t, is this invariant? And it is. This will be equal to the characteristic of the pre-image under t of A, which will be equal to the characteristic function of A, since A is an invariant set. So since it's invariant, then since we're going this direction in our proof, it is constant. All right, so our characteristic function is constant, which means only two things can happen. Either it is equal to 0 almost everywhere, which would then imply the measure of our set, which is equal to the integral of this characteristic function is equal to 0, or the characteristic function is equal to 1 almost everywhere, in which case, same thing, except now we're equal to 1. Okay, which is the definition of ergodic. We have an invariant set, and its measure is either 0 or 1. All right, let's look at the other direction. Okay. So we're starting off with a ergodic function. We're going to, an ergodic transformation. We're going to show that if we have a measurable function that is invariant, it must be constant. So we assume that our transformation is ergodic. And let's let f be a measurable function. We will also assume that our measurable function is invariant under our transformation. Once again, we're sort of going to find these level sets. Let's define A sub t equal to the set of all x in X such that f of x is greater than t for t in R. And so these are the level sets. You got your t values, and this is going to contain all of our points x so that our function value is greater than that t. Okay. Our goal is to now show that our function has to be a constant. So let's first consider the preimages of the A sub t's. What we'll work towards is showing that each of these level sets, A sub t, are themselves invariant, which means their measure needs to be 0 or 1 for every one of these level sets. And we will show that that only happens if the function f is constant. All right, so what is this preimage? By definition of preimage, this is all the x and x such that tx is in my level set. Okay. But by definition of what it means to be in that level set, this is all x and x such that f of t of x is greater than t. Okay. But we also are operating under the assumption that our function f is invariant. So this is all x in x such that f of x is greater than t. And this is just our definition of our level set. So we have shown that these level sets, AT, are invariant. Therefore, since t is ergodic, for each t in R, either the measure of the level set is equal to 0, or the measure of the level set is equal to 1. And this can happen if our function is constant. So if f is constant, then the measure of a sub t is going to equal 1 for all t less than c, and the measure of a sub t is going to equal 0 for all t greater than or equal to c. Okay. So if f is a constant, then we don't have a contradiction. We've got the measure of these invariant sets are going to be 1 and 0. But if f is not a constant, then there's going to exist a level set a sub t0 such that the measure of this set is going to be somewhere between 0 and 1. If they aren't all, it's not going to be all of our function, all of our x values. It's going to be some proportion of them. So such that 0 is less than the measure is less than 1. This is a contradiction. And so our function must be constant. All right. So let's scroll back up to the statement of our theorem. The statement of the theorem, or this lemma, gives us an equivalent or another characterization of what it means for a function to be ergodic. And there are two sort of variations of this lemma that can replace measurable functions by integrable functions and square integrable functions. So we only looked at the proof for it for measurable, but the same lemma holds that if you have any integrable function that is invariant and constant, any integrable function that is invariant is constant, then your transformation is ergodic. And same thing for square integrable. All right, so with this lemma, and specifically these variations of this lemma, we can now revisit our example of rotations of a circle, but this time look at irrational rotations. So irrational rotations are ergodic. Okay. So we're looking at the variation that involves square integrable functions. So given f and L2 of x, we want to show that if f is invariant under our circle rotation, then f is constant. Okay, so in order to do this, we're going to have to use the Fourier series and the equivalency in L2 between the function and our Fourier series. So because of this, we have our function is equal to its Fourier series, the sum from negative infinity to positive infinity of Cn times e to the 2 pi I nx, where our Cn is equal to the integral f of x e to the minus 2 pi I nx d mu. And again, this over here is the there's a u in there, Fourier series. All right, So we have this representation of our L2 function. Our irrational rotation can be written as x plus alpha mod 1. So if we take our Fourier series for the composition, this will be the sum, negative infinity to positive infinity, of Cn e to the 2 pi I n times x plus alpha, which is equal to, n goes from negative infinity to positive infinity, split up the exponent, e to the 2 pi I n alpha times e to the 2 pi I n x. Okay, great. We have these two Fourier series. And now we use the assumption that f was invariant under this rotation. So since we have our composition, f composed with r alpha is equal to f, then the two Fourier series, this one and this one, must have the same coefficients. Coefficients in these two Fourier series must be the same. So in other words, Cn must be equal to Cn e to the 2 pi I n alpha. And this is true if and only if Cn times 1 minus e to the 2 pi I alpha is equal to 0 for all n. Okay, so if this product is equal to 0, right, one of these two must be equal to 0. We want to show that it's the Cn part. The Cn part is going to be equal to 0 for n not equal to 0. And here's where the part that alpha, or the requirement that alpha be irrational, comes into play. So since alpha is irrational, all orbits of our rotation are infinite and distinct. Thus, in particular, the orbit of 0, which is equal to just n alpha mod 1, consists of distinct points thus n alpha mod 1 is not equal to 0 for all n not equal to 0, which in particular means for all n not equal to 0, we have this expression is also not equal to 0. I've left out an n in here, so let's make sure we put that in. Right, this should be 2 pi I n alpha, 2 pi I n alpha, 2 pi I n alpha, 2 pi I n alpha is not equal to 0. Okay, so this means that Cn must equal 0 for n not equal to 0. Okay, so if all of our coefficients greater than 0 in our Fourier series are equal to 0, what does that leave us? That means our function is just equal to C0 and is therefore a constant. Okay, so we have shown that if we have a measurable function, actually in this case, a square integrable function, that is invariant under the rotation by an irrational angle, then it is constant. And so by the lemma, this transformation, rotations of the circle, irrational rotations of the circle, must be ergodic. All right. Let's write down another definition. And this is the definition of uniquely ergodic. A transformation T is uniquely ergodic if it has exactly if there is exactly one invariant probability measure. And for circle rotations, the only invariant probability measure is the Lebesgue measure. All right. One of the big theorems in ergodic theory is the Birkhoff ergodic theorem. Okay. So for the Birkhoff ergodic theorem, we again have a probability space. We have an ergodic measure preserving transformation T. So T from X to X, ergodic measure preserving transformation. Then for any F in L1 of our probability space, shouldn't be a beta, should just be a B. What do we have? We have the limit as n approaches infinity of 1 over n, sum k equals 0 to n minus 1, f TKX is equal to the integral of f d mu for mu almost every x in x. And again, if we want to sort of say this theorem in words, we could say something like time averages converge to space averages. Okay, so in the context of our circle rotations, which you've just proved that if it's irrational, it's ergodic. So let's let R alpha be an irrational rotation. And let's set a set closed interval A to B. Then for almost every x in 0, 1, we have the limit as n approaches infinity of 1 over n. Sum k goes from 0 to n minus 1 of the characteristic function of our interval, and the rotation is equal to the measure of our interval, which is just b minus a. Okay. We can also make an equivalent formulation. In terms of measures of sets, which is the limit as n approaches infinity, 1 over n, sum k goes from 0 to n minus 1 of the measure pre-image intersected with B is equal to the measure of A times the measure of B. All right, I'm writing it down in this formulation because the next thing we're going to talk about, I think this is 4, is mixing. And here's the definition. Again, we have our transformation T. So a measure preserving transformation T will be called mixing if the limit as n approaches infinity of the measure of T to the minus n of A intersected with B is equal to the measure of A times the measure of B. So if we want to get a handle on what this might mean intuitively, let's assume the measure of A is greater than 0. Then the limit as n approaches infinity, the measure of this divided by the measure of A is going to equal the measure of B. And since we have the measure of this pre-image is equal to the measure of A, we have that the measure of this intersection divided by the measure of the preimage goes to the measure of B as n goes to infinity. And so what this is saying in words is the proportion of the measure of TNA which intersects B tends as n grows to the measure of B itself. So in particular, if you have two different sets that have the same measure, the proportion of this preimage that lies in both of the sets should be the same. So our preimage spreads out as n grows to become equidistributed all over their space with respect to the measure. That's sort of the idea of mixing, is that this preimage spreads as n grows to become equidistributed all over the space. With respect to all over the space with respect to the measure mu. All right, so if you think about, if we can scroll back up to our equivalent formulation of ergodic and kind of compare it to our formulation of mixing, you can kind of think of ergodic as being mixing on average. So this idea of mixing in itself is a stronger formulation. And if you're mixing, then you're going to be ergodic. So mixing, let's do this. We can write down that mixing, and we can hope that my iPad does not mixing, got to write slow, implies ergodic. Okay, so in order to show that mixing implies ergodic, we're going to start with an invariant set and show that the measure of the invariant set must be either 0 or 1. So let's let A be an invariant set okay? Then, since we are mixing, we have the limit as n approaches infinity of the measure of the pre-image A intersected with A is equal to the measure of A times the measure of A, which is equal to the measure of A squared. Okay. But A is an invariant set. So inside this parentheses, this is just equal to A. So this tells us that the measure of A is actually equal to the measure of A squared, which in turn implies that the measure of A equals 0 or 1. All right, so mixing is a stronger property than ergodic, and if you're mixing, it implies you are ergodic. The last definition I want to write down is the definition of weak mixing. Which says you have the limit as n approaches infinity of 1 over n times the sum as I goes from 1, nope, I goes from 0 to n minus 1. Now we're looking at this absolute value of our t to the minus I A intersect B minus the measure of A times the measure of B. This limit must equal 0. All right, so that is a bunch of the basic definitions and some theorems and the context of circle rotations that I hope you will find helpful. And feel free to send me any questions, and I look forward to meeting you this semester. All right, bye.